let's say we had the perfect data. There was no unfairness in the data that was collected. We created the perfect prediction model. No subgroup was neglected. Everything is very accurate. I just used the word that I said we should not use, accuracy, but still, let's say that all the performance measures are really good for all of the subgroups. Now we can go to the doctor's office and start using the model. And that's a lot of what we do, is to think about the way that these models are actually implemented in practice. I'll show you what we mean. So basically in medicine, prediction models have two main scenarios. Either they are a personal risk evaluation, like the example I've showed you, like the person that goes the green and the red. If the risk score is accurate, then I will get my treatment. And if it's not accurate, then maybe I will not get my treatment. That's a personal risk evaluation. But in many of the cases, what we do, that's the spotlight that we discussed with respect to preventive medicine. We usually use these prediction models in order to prioritize a group of individuals for some proactive intervention that we have in mind. And we have many of these. And we constantly have the need to define the subgroups that we're interested in. So the latter scenario, this scenario of choosing a specific set of individuals for some proactive intervention, we need to take the result of the prediction model and to basically decide which individual goes into that group that gets the proactive intervention and which individual does not. An example of how we do that in practice before we talk about the fairness considerations. Sorry. So the way that we do that in Clalit is through a population management system that we created, still working on creating, which is called CPI, Clalit Proactive Preventive Interventions. And that system basically looks like this. For each, I see there's a bit of a problem with the direction of the text, to ignore that. But for every physician or GP, primary care physician within Clalit, there is a population management screen in which he or she has all the different clinical conditions that are currently within the system. And for each clinical condition, we see the list of patients that are relevant so for here, it's osteoporosis, and we see all the different patients that are relevant for that condition. And the way that they are ranked is using the prediction model. And so, and the other thing that we have is, you see these pink squares? It says proactive focus near these little pink squares. So within Clalit, the way that we use this system is that every GP gets 2 hours every week in which, again, he or she can block the schedule, not get any new patients that come in through the door, complaining on whatever brought them to the doctor's office that day. But instead, we do proactive medicine, which means that we block these 2 hours, and then the physicians can use this system to see which patient actually needs their intervention in a proactive manner. And how do we choose the specific patients for that intervention? We mark them with those little squares of pink, marking that they are at a specifically high risk, and we mark these patients as candidates for proactive focus, meaning that if we have these 2 hours a week, these are the patients that we should concentrate on or focus on during these 2 hours. So I'm telling you all of this so you will feel how important it is that we identify the correct patients in order to mark them as candidates for proactive focus, and how it's important that we identify the correct patients with respect to the priority rank that we give them within the system. This is another view that it's more holistic. I've just told you about the view or the priority rank within a specific clinical condition. We also have the same kind of thing in a holistic manner, but it doesn't really matter. A holistic manner meaning taking all the different clinical conditions that are relevant for each patient simultaneously, but it doesn't really matter because it's the same kind of idea that we have to prioritize the correct patients for the intervention. So now let's take a scenario. We have Dr. Jane Smith, who is a GP, and she's responsible for treating, let's say, 1,700 patients. Let's say that we created a cardiovascular prediction model, which identified patients at specific high risk for heart attacks and strokes, etc. And we applied that algorithm to about 1,000 individuals at the relevant age group for that intervention. And now we estimate that she can proactively treat, say, something like 30 patients who are specifically high risk for cardiovascular disease within the next year. And now we need to decide which patients are prioritized in that list, which patients will get the status of proactive focus and not just regular care. So what do you think? We have the prediction model, we have the result. Each patient within the list of the patients has a number between 0 and 100%. Which patients should we concentrate? Which 30 patients should we choose?
So you only have estimate of the risk. You don't have estimate of the likelihood she can help, right?
That's a very good comment. That's a very good comment because we don't have the causal estimation that we are likely to help these patients or how likely we, and that's very accurate. But let's say that this causal estimation is hard to estimate. So we use this prediction model as a proxy to identify the correct patients that we should treat. In many cases, what I've just said is accurate. We use this proxy. Sometimes we do use causal estimations, but in a very manual way, in a very like rule-based manner of when the physicians tell us what specific criteria they think are relevant and which patients are good candidates or not. But let's say that within the group of patients that the physicians defined as relevant for the intervention, say the relevant age group, like we have here, we usually use the prediction model because it's much easier to estimate. And we'll talk about the challenges of causal. I hope we'll have the time, but we're planning to talk about it at least some of the remaining time. So let's say that we do use the prediction model. What do you suggest? How do we prioritize?
Can you say a little bit more about what happens when you treat somebody? Like, what are the pros and cons that will happen to them as a result of being treated?
Let's say that it's a perfect treatment, like the HCV treatment. Okay, let's look at the HCV example. It's a perfect treatment, almost no side effects, more than 90%, 98% cure, and no negative outcomes.
Is there some notion of affirmative action where you prioritize the socioeconomically underprivileged more because the socioeconomically wealthy will do their own proactive thing without the doctor reaching out?
So that's a very good question. It's a philosophical question, but it's okay because this is the philosophical part of the debate or the discussion. And I'll say that we're not quite there yet. I'm not sure if it's right or wrong, really. But it does take us to the direction that I want to go, which is philosophical considerations of who should be prioritized in those kinds of intervention lists. So usually...
Sorry, just a comment. If the treatment is so nice and completely free of anything, what decisions are there to be made? Just prescribe it to the whole list and be done. It takes less than 2 hours.
So, yeah. So let's say that in real life, physicians are just overloaded. And I can think about dozens of clinical conditions that are currently something that I need to screen for, I need to proactively try to prevent. And I just can't do everything for everyone. It's just not effective. Even for the hepatitis C, which is a classical example, because all I'm doing is sending these patients to a blood test. So the intervention, the test is not dangerous. If they are identified as positives, I have almost the perfect treatment to give them. But still, the whole process costs money. If I focus on these patients and put all my efforts on preventing hepatitis or identifying hepatitis C silent carriers, then I'm not treating or trying to prevent cardiovascular events because I'm not putting time into treating those conditions. So you need to know the medical system in order to understand how loaded it is and how little time we have to devote to these proactive actions, because usually most of medicine is reactive. These physicians sit in their office and get to see patient by patient based on whatever the patient decided to come with this day that bothers him or her that day. So the amount of time that we can actually devote to something proactive that's a limited resource, and we need to allocate that limited resource in a smart manner. So usually, so you're not the usual audience, but usually the first answer that people will say, okay, I have a prediction model. I'll just rank patients based on the absolute risk in a decreasing manner. I'll take the top 30 if that's the capacity I have. That's the amount of resources they have to allocate. And those are the patients that I will treat. So this is a simulation of risks based on age and sex groups of cardiovascular disease. So it's not real data, but the simulation is based on real averages and standard deviations of risk within that subgroups, those subgroups. So, okay, this is what we get when we do that. And if we look closely into the list, what we see is that almost everyone in this list are males. And we have one female. And the average age of these people is more than 80 years. And now it begs the question, are these the individuals that we want to focus on when we put all of our efforts on preventive medicine with respect to cardiovascular diseases? So I can tell you that's a true story. When I first saw this list, I thought that it seems really unfair because the females and the younger individuals have very low chance of getting into that list, because everybody who has the highest risk are males, and the average age is pretty high. So what I thought would be reasonable to do is to basically create a percentile of risk within each age and sex group, and then rank the list based on the column, which is now marked as green, which is the percentile within the age and sex group. Now the list, at least to me, it seems much more diverse. It has many more females, so now it's much more balanced. And the age is much younger. Now we give opportunity to patients who have relatively very high risk with respect to their age group, but we give an opportunity to younger individuals to get into the list. For me, this seemed much more reasonable, and it seemed more fair, and that's the way I thought we should implement that list. Meaning that's the people we need to, or that's the criteria we need to use in order to get people into that list. And I can tell you that after discussing this with some people who are experts in the field of philosophy, at least what I was convinced is that there isn't a single philosophy theory that supports the fact that we're doing this because of, let's say, these two individuals. So look at the list. Look at the first list in which Mr. Stanley is a part of, and look at the second list in which Mrs. Greer basically took his place. So she did not directly take his place, but he is not present in the second list. Now look at their details. They're both at the same age group, and he has a higher absolute risk of getting the intervention. He has a higher absolute risk for the outcome. Is it reasonable that just in order to make the list more diverse with respect to sex groups, we actually prefer to treat her instead of him when he has the higher absolute risk? And it turns out that even though it seemed very reasonable to me when I looked at those lists, there isn't a single philosophy theory that supports this. or stream of philosophers that support this. As opposed to that, the fact that we prioritize based on age groups is something that is highly supported by philosophy streams that measure intervention in terms of how we promote the overall good that we do. So if we think about the healthy life years that we could get if we treat these patients and actually prevent the next heart attack or the next stroke, then if we treat a 50-year-old and gain 30 or 35 years of healthy life years, as opposed to treating someone who is 82 years old, then many philosophers will agree that that's very justified. And that's a very good way to utilize the resources that you have, which are limited, and you need to allocate them in a manner that will improve the overall benefit that we have in society. So, yeah.
Hi, but didn't you previously say that women are less likely to be in the, are falsely less likely to be thought of as having risk for, say, a heart attack? So shouldn't this kind of take that into account as well? Isn't that correcting the low risk that women usually get for heart disease?
So I'll have someone in the front repeat the question. Because
the question was kind of bouncing off of your previous statement that women are underdiagnosed for heart disease, and the risk estimates for the women might be too low, for the females might be too low. Is that something we should take into account?
And are these numbers multi-calibrated?
These are multi-calibrated by definition because they were created by the simulation from the, but are they calibrated with respect to the real biology? And that's a very good question. Whether the fact that we know that women are underdiagnosed specifically for these conditions, meaning that we have to correct for that. And I think that's a very compelling argument. Maybe it's a good argument. The place which is hard for me to take that argument and act upon it is that I don't know the proportion. I know that there is some misdiagnosis or underdiagnosis of PMS, but I don't know to what extent. And there's so many factors. So I also know that maybe in some groups of society, there is underdiagnosis because they just don't go to the hospital when they don't feel well. And maybe in the periphery, when the access to hospitals is less immediate, that's also the case. What I'm trying to say what I'm trying to say with all of this part of the presentation is that these are really hard questions that I don't have very good answers for. But when we utilize these models in practice, we have to make some decisions. So I can tell you that, again, and that's my personal view, it's easier for me to go with decisions that are objective, that I don't start to take into account things that I can't measure, like underdiagnosis, because that's just it's endless. I'll never get to the perfect decision. So I will try to maybe look on percentiles of risks compared to age. Maybe in some conditions I won't. But the thing that I'm trying to say is, if you actually create these prediction models, there's a lot of decisions to make after the prediction models are calibrated and are developed. And in the way that you utilize them in practice, there's a whole lot of fairness consideration to take into place. And it's not easy to make the correct decisions. And with respect to the first question that I received in this part of the talk about, wait, this is all prediction, it's not causal. Who says that those at the highest risk are actually those who will benefit from the treatment, and the treatment will actually be effective for these patients? Then for these kinds of things, since causal estimates, as opposed to prediction models for which I can actually calculate the performance on a test set and think I know how well I perform. With causal, I never know if I get it right. There's always the possibility of hidden confounders. And I'm starting to think that maybe we won't get to that part of the talk, but there's always the possibility of hidden confounders. So we don't usually use causal estimates in order to make clinical decisions yet. I think we will get there in a few years when we find the right way to do that. But currently we use prediction models, and the causal factors that we put into the decisions are based on guidelines, and the places where the guidelines say this is the group of individuals who are eligible and are good candidates for the treatment based on randomized clinical trials that we've conducted. And within the scope of the guidelines and recommendations and the clinical judgment of the policymakers, then we imply these prediction models. And just to say that there is no right and wrong answer here. There is a lot of thinking that we need to seriously put into that phase of the process, in addition to the collection of the data and the creation of the data and the modeling. Just don't forget that part. Now we have two options, and Guy and Cynthia, I will defer to your judgment. We can talk about the interesting way in which we use multi-calibration in order to create the COVID model, which had nothing to do with fairness, but it's an interesting use of that model. Or we could talk a bit about causal and how causality and being familiar with the causal analysis can help inform subgroups, different age and sex subgroups, and different comorbidity subgroups with respect to medical interventions, and be more fair towards those subgroups. So I'll defer to your judgment. What do you think?
Option 2, we agree.
Option 2 it is. Okay, so I'm skipping. Just say that if someone wants to know how multi-calibration can help develop a model when you don't have individual level data regarding the outcome that you're interested in, as we did in the beginning of the corona pandemic, you can read this paper, and it was pretty cool. And we have Guy to thank for this model. So if you want to, I highly recommend it. So causality analysis for everything I have just said. It'll be pretty quick, but I think we have enough time in order to make it coherent. So when we have a new virus and we have a new intervention like the vaccine, and we want to know whether the vaccine works or not, because that's the decision that every one of us needs to make when they need to choose whether or not they want to receive the vaccine. Then we want to know a lot of things about this vaccine. Is it effective for us? Is it safe? Is it safe for specific subgroups, say children, pregnant women, the elderly, those with multi-comorbidities? Do we have waning immunity? Is the vaccine effective for novel variants that keep coming up? So we have a lot of causal questions that we really want good answers for, because they really affect our decisions tomorrow morning regarding our actions. So RCTs, randomized clinical trials or control trials, are the first line, and they're the gold standard, because in these trials, we randomize the patients to two groups. One is exposed to the treatment, the other is not exposed to the treatment. And since everything was randomized and we have, say, large enough numbers, then we think that we know that every difference that we see in those two subgroups with respect to the disease that we're studying is as a result of the intervention or the exposure that we studied in that RCT, vaccines in this case, and no hidden confounders, and everything is accurate. The problem is that these gold standards are expensive, they are slow, they are with highly selected populations, usually not children, not pregnant women, not the elderly, not those with multi-comorbidities, just the everyone else. And sometimes we just can't do them. So, okay, we can't test whether or not, cigarettes are healthy for you or not, because it's not ethical to expose patients to cigarettes, now that we know that they're not. So sometimes RCTs just not give us the answer, and we need to use something else. And here, observational studies are the other manner in which we can try to estimate causal effect. The thing about observational studies are that in this case, we just use whatever data that we have, and the reason that they're called observational is that we just observe the data as it is. We do not get to manipulate the treatment assignment. So people choose to get vaccinated, other people choose not to get vaccinated. And then based on that decision, which we did not control, we're trying to estimate the causal effect. And this makes it a challenge. It says here identification. We'll see that what that means in a minute. And specifically for subgroups, RCTs are really not effective because the numbers are usually small. It's sometimes it's a few hundreds, sometimes it's a few thousands, but it's not more than that. And that gives us the opportunity to evaluate an average treatment effect, the average effectiveness of the COVID-19 vaccine. But it's really hard to estimate how effective that vaccine is for different subgroups if we think that it may be different for different subgroups, and that's called treatment heterogeneity. So sometimes we think that the effectiveness will not be the same, and we need to try to estimate that, and that's a problem with RCTs. And in addition, so we said that basically that some groups are just completely excluded from RCTs. So pregnant women, for example, and in pregnancy, there are all sorts of weird things that happen to the immune system. So it's completely plausible to think that the vaccine works completely different for pregnant women because the entire system, the entire immune system changes in order to not attack the baby that grows within you. So it's different. Do we know that the vaccines are effective, or do they have the same side effects they have in other individuals? For pregnant women, we don't know because pregnant women are excluded for ethical reasons from these studies. The same goes for all the different subgroups that we've just discussed. And that begs the question, and I think it's a fairness question of how can we empower individuals in those subgroups to make informed decisions regarding whether or not to receive the vaccine if we don't give them any information that is relevant for them based on their RCTs. So here we use observational data, and because in observational data we don't have, it's not costly because it's already there, something happened in reality and we're just measuring it, it's much cheaper and we can use much larger sample sizes. And for that reason, they're very good at estimating subgroup effects. And I think we've stated all of this. And let's try to understand why it's challenging, because we understood why it's needed and we understood why it may be even fair, but why is it hard? So the question is, a causal effect, or that's not a question, that's a definition. The causal effect is the contrast between two potential outcomes. What would potentially happen to me, to Noah, if I contract COVID-19? Would I get COVID-19 if I get vaccinated versus a potential counterfactual future in which I did not get the vaccine? And by definition, only one of these futures can happen, and only one of these potential outcomes can be observed, because the other one is what we call counterfactual. So imagine a person will have to split the person in half and treat half of the person and not treat the other half of that person in order to get the true causal estimate. But obviously that can't really happen. So what does happen in practice, that we're trying to study the causal estimate from those who happened to receive the treatment and those who happened not to receive the treatment. And those are two different groups of individuals. And the causal identification is the process of making the jump from this observed data to the counterfactual contrast of whether I got the vaccine or I did not get the vaccine. But the thing is that these two groups, the blue people and the orange people, are not the same. In real life, we do not have randomization. So in real life, patients who chose to be vaccinated and patients who chose not to be vaccinated are not the same. I can't just measure the amount of COVID-19 or the incidence in COVID-19 in these two subgroups and compare it. So I need to somehow overcome the differences, the inherent differences between these groups in order to study the causal effect of the intervention that I'm interested in. And the causal assumptions the assumptions we need to, in order to make causal inference are, and the first is the most important one, so listen carefully. The first is called exchangeability or ignorability. That means I'll define it more accurately in a moment, but basically it means that we need to find groups, the red people, the green people, and the green, we had blue and orange, right? So the blue people and the orange people, I need to find groups of blue and orange that are identical with respect to everything I think may affect the causal estimation, and just compare within those subgroups. I need to find groups that are exchangeable or similar enough so I will know that the difference that I'm measuring is with respect to the intervention that I'm interested in and not with respect to different other different characteristics that we have. And in other words, we could say that the treatment assignment is independent on the potential outcome of what would happen with each of the treatment assignment. Obviously, we just said that it's not true. It doesn't mean that it has to be true on the raw data or the basic groups that receive the vaccine. We just need to make sure that it's true within strata defined by a set of potential confounders, meaning variables that could affect both the exposure and the outcome, and that thus may cause spurious correlation in the data. I'm skipping the next of the assumptions. They are important, but not as much as the first one. And I think that the first one is the most, that's the intuitive part that we need to understand about it. So RCTs have it easy. They have exchangeability because they have randomization. So the groups are exchangeable because if we have a large enough sample size, we can assume that any other variable that is relevant and with regards to the outcome will just be distributed similarly between the study groups. And that's why we'll have exchangeability. Again, skipping the other assumptions. But in observational studies, by definition, we need to work hard in order to get to exchangeability. How do we do that? And I'm sorry that I'm doing it a bit quickly, but I think you'll get the point. The thing is, we need to identify a sufficient set of confounders that may create spurious correlations. A confounder is a variable that is related both to the exposure that I'm trying to study and the outcome that I'm trying to study. So in this case, high temperature is correlated with ice cream sales. It is correlated with shark attacks, but obviously we don't think that ice cream sales causes shark attacks. Okay, if we will stop selling ice cream at the beach, the sharks will not stop their attacks. Why do we see a spurious correlation between these variables? Because we have this variable that is called high temperature. If we ignore that variable, we will not measure it, and we will not say, for example, see the correlation within different seasons of the year. We might think that ice cream sales causes shark attacks, but it's not really the case. So when we're trying to study the exposure of COVID-19 vaccines on the outcome of say, COVID-19 infections or severe disease or death, then we need to think about all the potential variables that are correlated both with the exposure and the outcome, or cause both the exposure and the outcome. And in order to do that, you have to use domain expertise. This is not data-driven. This has to be based on domain expertise. And you need to know what happens in the setting that you're trying to study. So for us, we knew the different demographics that affected the vaccination. We knew the different differences over time. And we knew what factors we have to try and measure in order to capture all that. So for example, we knew that the confirmed cases changed by day, but also by different groups of age. We knew that different groups were vaccinated at different times. We knew that groups at higher socioeconomic status, for some reason I said that I only had one piece of Hebrew. One of the English tables was deleted, but so on top of one it says poor people, and below where it says 10, it's rich people. Okay, and what we have here is the amount of vaccinations, and on the right, another missing label is the amount of the incidence of COVID-19 before the vaccination campaign. So you see that the higher socioeconomic status both get more vaccinated, and they had less incidence of the lower incidence of the disease before the vaccination campaign. So this is not fair, obviously, but this is the reality, and we have to deal with this reality when we're trying to study the effectiveness of the vaccines, because we may think that the vaccines are very effective just from seeing this picture, but we know that these incidents are before the vaccination campaign. So it means that the low incidence for the high socioeconomic group is not because they were more vaccinated, it's just because they were more careful, they live in different circumstances, whatever. So when we're trying to study these effects, we have to take into account all of the potential confounders and decide to control for them in some manner. I will skip the different manners that we could employ, but we could use multivariable models as one of these manners. But we can also use something which is a bit low tech, which is matching. And we can try to match individuals very closely with respect to these variables in order to be able to create two groups that we actually feel are exchangeable, because we know we have the domain expertise of knowing which factors are relevant. The way we do that, and that's very important, we never go to the end of the follow-up period and just match individuals based on these factors, because that's wrong. That's peeking into the future, and that's different from what would happen in the trial, and that's introducing bias. But what we actually do is to try to emulate the clinical trial by recruiting patients gradually over the follow-up period, only looking at the data that is available to us as of that date. So we gradually go and recruit people, and we could recruit a control, which one day goes and gets vaccinated and stops being a control. And that's very important, because when we do that, we try to avoid all sorts of biases that could result from peeking into the future. So now imagine that we created like digital twins that are very similar to one another with respect to all of these variables, with one difference, which is the vaccination status. Now we can try to study the effects. And the question is, how do we know? How do we know that we identified all the confounders and we did not forget anything? That's why I told you before, we can't do that. We never know. There's always the potential that there is some potential hidden confounder that we did not think about. And so we come up with different ways of trying to understand whether or not we did a good job. And one of these ways is called negative control outcome. And if you look closely on these incidence, cumulative incidence curves of the vaccinated and the unvaccinated, based on the matching process that I've just showed you, and you look closely on the first days of the follow-up, you see that the incidence in these days is very similar between the two study groups. There isn't any mechanism that will make these two groups very similar in the first few days after receiving the vaccine, when we know that the vaccine cannot take effect yet, and will disappear after day 12 or day 14 of the follow-up. So if we get these groups to be so identical in the first days of the follow-up, when we know that the vaccine should not take effect, and then we see an effect, we are pretty confident that the effect that we see is with respect to the intervention and not something else. So just like brief running through different estimations. So in this manner, we were able to find out for the first time in the world whether COVID vaccines are actually effective in real life or not, and specifically whether they are effective for different subgroups. For example, we found out for those with multi-comorbidities, the effectiveness were not 95% as they were in the clinical trial, they were 81%. And for different patients with different comorbidities, the specific comorbidities, you can see the numbers. Again, the effectiveness was lower than it was for the average population that participated in the trial and did not represent these people. We were also able to study the effectiveness for pregnant women, which were completely excluded from the trials, and find out happily for those in that case that the effectiveness is as high as it was in the RCT. We could study the different side effects and find out, for example, that the main side effect that we found and was not known before it was found in Israeli studies, myocarditis, for example, is completely different with respect to different age and sex groups. So for young males, that's the higher incidence of that side effect, as opposed to females, for which that side effect is almost completely not relevant. So if I'm a mother and I'm considering to vaccinate my child, it's very important when I'm making that decision. It's very different if my child is a boy or a girl. I can tell you I have boys and they were vaccinated, but those kinds of pieces of information, causal estimates, were really the kinds of pieces of information that we, when we discussed with the patients and people that approached us and asked whether or not to get vaccinated, these are the pieces of information that were used in the individual decision. These are the individual pieces of information that were used to empower the individuals to make their own decision of whether vaccinating themselves or their children is right or wrong for them. And that's with respect to subgroups, but that also allowed us to know whether the booster doses, the third booster and the fourth booster, are effective. And I think that with this, we can conclude. So we discussed prediction models and the different stages of creating prediction models in which you need in practice in medicine to think about fairness and how to approach that. And we talked about how causality and getting to know that type of analysis really can help you open a different way of thinking about fairness towards subgroups, because usually RCTs just don't give the answers relevant for everyone. And I think that with this, I can end my sharing of the screen.